Welcome back. So in this series, we have kind of broken up the gigantic field of reinforcement learning into a number of subfields. So model-based reinforcement learning, model-free reinforcement learning, on-policy, off-policy, gradient-based, gradient-free. And today we're going to be specifically talking about model-based reinforcement learning. This has a really rich history in optimization theory, dynamic programming, nonlinear dynamics. A lot of this came about from Richard Bellman's Bellman optimality condition and dynamic programming. So Bellman made a huge impact to the field, coming up with these kind of optimality problems, showing when you can solve subproblems and still get a globally optimal solution. And those are still being used today in these policy iteration and value iteration algorithms, and in optimal nonlinear control using the Hamilton-Jacobi-Bellman equation. So specifically today we're going to zoom in on this block here, and so we'll be talking about how do you kind of iteratively optimize a policy or a value function by solving subproblems with dynamic programming. And so this is in the context of a Markov decision process. We assume that the environment that our agent is interacting with is a Markov decision process, so some probabilistic state transition process. Okay, and I'm going to jump in. To give you the details of dynamic programming and policy iteration and value iteration, I first want to just recap the really basic stuff for reinforcement learning in case you're just tuning in. So our agent is interacting with an environment. It senses its state through a series of measurements S at time 1, time 2, time 3. This is an iterative measurement process. We're assuming a discrete system like playing a game of chess where it's turn-based. And at each time, I get to decide on an action to take A to try to hopefully maximize my future reward for this game. And we are trying to design an optimal policy pi, again, that gives us the maximum future rewards. We have this value function v that, given our policy pi, it tells us how advantageous is it? What is the expected future rewards of being in this state now and enacting this policy pi? And it's a probabilistic process, so we're taking the expected value of our future rewards given some policy pi. And I don't know the best policy or the true value function for that best policy out of the gate. That's what I'm trying to learn. I'm trying to learn the optimal policy and ideally also an optimal value function for what is the best state to be in. What we do assume that we know at the outset, at least for this model-based reinforcement learning, for kind of the simplistic version, is we assume that we have a model for how the environment works, how the system works. So we assume that the environment evolves according to a Markov decision process. So that would be this probability here. So the probability that the state of my system at the next time step will be S prime is some probability based on or conditioned on my state currently being S and my current action being A. So given a current state S and a current action A, there is some probability that my system will transition to a new state S prime, and that's encapsulated in this probability model P. This is called a Markov decision process, and it generalizes a normal Markov process to have this action or control input A. We also assume that we have some model of what the reward structure looks like. So what is the probability of a reward given some current state S, or sorry, given a current state S and a current action A, and assuming that I move to a future state S prime in the next state, what is my expected reward given all of that happening? So given kind of this information, what is my expected reward at the next time step? And again, this is kind of an assumption that you know the rules of the game you're playing. So if I'm playing chess, for example, the reward only comes at the very end of the game, but I know what the rules to win are. I know how to checkmate someone or how to not checkmate someone. You have to know that going in to play. And so this would basically say, I know what my reward is given a current, given a future state. And so this is the information we have at the outset, and we're trying to learn an optimal policy and an optimal value function that kind of allow you to best play that game to maximize your future rewards. Good. And I'm going to walk through some properties of the value function that allow you to solve this problem. This seems like a big brute force problem. Let me take one step before I go into the value function. In the game of chess, for example, there are so many possible board configurations. The state S, there are so many possible states that your chessboard can be in, something like 10 to the 80. In fact, fun fact, the number of possible boards of chess that you can have is an unknown number. We know that it's very large, 10 to the 80 or something on the order, but we don't know exactly what that number is. And I think that's kind of a fun fact that we know it's huge, but we can't actually perfectly quantify what that number is. It has someone famous's name, but that's neither here nor there. And so we can't actually compute this optimal value function at all of those 10 to the 80 board conditions. So to solve for the optimal policy and to get this optimal value function would be a combinatorial, like brute force search over all possible states, and it just isn't even remotely feasible. Okay, so we need some alternative. And that's what the dynamic programming is going to allow us to do, is to break this up into smaller subproblems so that I can think of like, what's the optimal thing to do for 3 steps ahead, or for 4 steps ahead, or for 5 steps ahead. That's actually how you learn to play when you're a kid, is you think a couple moves ahead and you optimize for that. That's what dynamic programming is going to allow us to do, break this up into smaller subproblems. Okay, and so again, the goal is always to optimize the policy to maximize future rewards. That's all I can do as an agent. So we start with this value function. Given some policy pi, the value function at a given state S is my expected future reward, discounted potentially by some gamma factor. So this gamma is a number between 0 and 1 that discounts future rewards over current rewards. And that's kind of an economic principle. There's results that show certain optimality and convergence criteria for this kind of exponential decaying reward function. But that's what the value function does, is it basically adds up your expected future reward, given that you're in a state S now, and your first state is S, and you enact an optimal policy pi. So it's kind of an implicit function of pi. And if I drop the subscript pi, if I just talk about the value function, capital V, then this capital V value function is the value of being in a state S, assuming that I am working on the absolute best possible policy. Again, for any game that you can name, like chess or Go, like most games, you have no idea what this best policy is, but there is some hypothetical best policy pi, and if you always played that best possible policy pi, this V would be the value of being in a particular state, assuming you do the best thing possible. Good. And one of the really, really cool things, so this is what Bellman figured out. Richard Bellman, the rest was history. He figured this property out that allowed him to invent dynamic programming and a large part of the field of reinforcement learning. So this value function here, this exact expression, you can take this sum of future rewards and break it up into the current reward at time step now, 0 means now, plus all of the future rewards starting at time step 1 to infinity. So I take my sum of all of my rewards at time now to infinity, and I break that up into my reward now, plus the sum of all of the rewards at the next state to infinity. So now, this is the reward given that my current state at time now is S. This is my reward given that my next state, S1, at the next time step is S prime. And so what this allows you to do is essentially rewrite your value function. Your value function, given the best policy possible, is whatever your current reward is, plus a discounted value function at this next state S. And so you can recursively define your value function like this. My value function at my current state is a function of the value function at my next state, S prime. And that's really, really powerful. So this means that if I do the absolute, if I know what this value function is, and I know what the best next state is, All I have to do is take an action now to get me to that next best state in the future. And so this is a recursive expression that allows you to break it up into subproblems. This is called Bellman's equation, or Bellman's optimality condition. And if this is satisfied for a problem, if the value function, the thing you're trying to optimize, is a recursive function of itself at the next time step, you can break this problem up into subproblems. You can optimize locally, and if you optimize locally enough at all of these different states and you put them together, you still have an optimal solution. So basically, I can optimize this subproblem and then plug it into this problem, and it's still optimal. That's really simple but very powerful. And once I have my optimal value function, so assuming that I just, I did this and I had this optimal value function, and maybe someone handed me an optimal value function, then I can always extract from this, this expression here, this optimal value function, I can always extract the policy pi as the pi that maximizes this expected reward. It's a little circular. Here we're maximizing over the policy pi, this expression. Argmax means the pi that maximizes this expression. So you can always extract a policy from a value function. Okay. And given a policy, you can create a value function. So this is Bellman's equation, and this is the basis of dynamic programming. So dynamic programming is how we solve, how we build up this value function. Again, we assume we know the rules of the game, but we don't know the value function or the optimal policy pi. And so we can build this up even for complex games using dynamic programming, as long as this equation is true. And it's true for Markov decision processes. So what Richard Bellman said is essentially, given systems that are recursive subproblems like this, you can break them up, this multi-step optimization problem, like how do I make a sequence of chess moves to win a game, I can break that up into a number of smaller subproblems, where if I optimize over those subproblems and then I put them all together, I still have an optimal action policy. And there's a lot of details of dynamic programming, kind of how you program this up in a computer, how you actually do this. Maybe that'll be a detailed lecture for another day. There are kind of two big approaches. There is the top-down approach and the bottom-up approach. And so in the top-down approach, you essentially list out all possible subproblems. You kind of list out all possible little subproblems, and you try to solve all of them. And you basically just keep track. Every time you need a subproblem, you see if it has been solved. If so, you use it. If not, you solve it. And recursively, you end up filling out this table of subproblems until eventually you've kind of brute force solved the whole thing. I'll point out, you can't solve chess using dynamic programming. It's too big. You have to use other approximate methods, things like deep learning and things like that. But it's a good cartoon. You can solve tic-tac-toe using dynamic programming. That's one of my homework exercises. So the top-down approach is basically to create this table or memoization of all subproblems and solve them as needed until they're all solved. The bottom-up approach is basically to always start with the smallest subproblems and work your way back, aggregating them into bigger problems. So the way you would think about that is you would start from every winning configuration, every configuration where you definitely got a reward and won, and then you'd optimize one step back. What was the best move to get me in that position? And then you'd optimize 2 steps back. What was the best move, given that I want to be here, to get me in that position? And you'd kind of recursively build up bigger and bigger optimization sequence from these winning configurations or from locations where you know you're getting a reward. This is a massive simplification, but that's the basic idea of dynamic programming. And although it's still very expensive and kind of a brute force approach, it's still better than a naive brute force approach. Dynamic programming is really closely related. For those of you who are computer science people, it's closely related to divide and conquer methods, except that divide and conquer methods like the quicksort algorithm specifically rely on your problem being non-overlapping and non-recursive, whereas this is a recursive optimization, so this is a bit more sophisticated. Okay, that was a lot. So now let's talk about how we actually do this for value iteration, for example. So two of the leading algorithms that rely on dynamic programming for model-based reinforcement learning are value iteration and policy iteration. And so value iteration is essentially going to allow me to use Bellman's optimality condition to iteratively build a refined estimate of my value function through trial and error. Not through trial and error, through optimizing a sequence of events through a known model. And there's ways of tweaking this so that you can do it through trial and error. That's called approximate dynamic programming, and I'll talk about that later. So the idea is that the value function, again, we're trying to maximize over all of the possible actions. We're maximizing that action to give this optimal future reward. And so it's my reward now plus a discounted value function at the next step in my model given that action A. And I have to sum up over these probabilities because this is a Markov decision process. So if this was a deterministic process, you wouldn't have this sum and this probability, but this is essentially necessary because this is a probabilistic Markov process. But this is the thing we're trying to maximize over is our future total reward, which is my reward now, given this action I'm about to take, and my future value function, the sum of all my future rewards discounted by gamma. This is literally just this here rewritten. And so what we're essentially going to do is kind of iteratively start to update this V given this situation. So we're going to, in every subproblem, assuming that this assumes two things. It assumes that I know the model of where I will be given an action from my current state. And it assumes that I know V at my next state. So I basically create a big table of my value function at all of the possible states. And I might initialize it at 0 or random or whatever. And then what I do is I start at a state. So I randomly pick a state. I start there. And I start kind of playing the game. I start running through action sequences and updating my estimate of the value function. So let's see how this works. I'm in a state S now. And what I'm going to do, I actually can evaluate this function for all actions because I know the reward function. I know the model P. And I at least have a table of what I think the optimal value function is at all next states. Now that might be a really crummy estimate. This is kind of a V hat. This is an estimate of the value function. It might be a garbage estimate, but it's something, it's the best I've got. And so what I'm going to do is I'm going to maximize over all actions. I'm going to compute this for all actions and pick the best action that gives me the maximum possible value, assuming this bad estimate here. And I'm going to update the value function at this current state S that I'm currently at. I'm going to take my table, find my current state, and I'm going to update that value function with this maximum expected future reward. Then I take the next step, and I do the whole process again. Now I'm in a new state, and I find the best action. This assumes that I have some estimate of what my value function is at the next state. And I do this again and again and again. And even if this value function was initialized badly, when I run through this time and time and time again, I'm going to iterate through this. That's why it's called policy iteration. I iterate through the game. I play a game of chess. I play another game of chess and another one and another one and another one. And each time I'm updating my value function based on what I think is the best action. This is on policy, if you like. And so eventually that value function starts to get better and better and better. And the better the value function gets, the better I'm able to update my value function because this is a recursive formula. It's a really simple idea. Because it's recursive, I can just initialize everything poorly and then iteratively kind of refine that value function as I play the game and play the game and play the game. And I'm kind of virtually playing the game, a simulated version because I know the rules and I know the probability here. So this has to be, you have to have a model to do this value iteration. You need to know P, and you need to know what is the expected S prime, the next state, given that P. Now, in this case, once I've done this, so I iterate over my policy, I play a game, and then I reiterate. I play another game, and I play another game. Maybe I start from different random board positions, and then I play and I play and I play. And I iterate until this converges to within some tolerance. Now again, you can't do this for exceedingly large problems where the state space is, billion or trillion or 10 to the 80 like in chess. But for small problems like tic-tac-toe, you can actually code this up and try it yourself. Okay, so I highly encourage you to enumerate all of the states of a tic-tac-toe board and just initialize some crappy random initial value to every possible state, and then run through this value iteration, some big for loop, until you refine that estimate. And once that's converged, you can then extract the optimal policy as the A that maximizes this thing you've been working with, this thing here. So that's value iteration. And this relies on Bellman's optimality condition, and it uses dynamic programming. It's a type of dynamic programming. So the kind of other leading approach, so that was value iteration. Policy iteration is just a little bit more complicated, but also very similar. And it's a two-step iteration process. So what we do is, the first thing is we lock in a policy pi. So it's whatever we think is the best policy pi. And we iteratively update our value function locking in that policy pi. So we do the exact same thing as before, but instead of doing the max over all actions A, we just enact our whatever we think our best policy is. And again, we kind of iteratively update what the value is for every state by walking through different states and seeing what happens, essentially. And then we lock in that value function. After we've iterated on that, we lock in the value function. And then we sweep through the actions, and we try to iteratively update the policy so that given a state S, we can take the best actions A that maximize our future rewards. Now again, that assumes that I have a good working model of my value function at this state and at all future states, at the next state S prime. Now again, this might be a bad approximation of the value function here, but it's usually good enough to improve my policy. Then once I improve my policy, I lock my policy and I do another value iteration step. And that might be still a crappy policy and a bad estimate of the value, but it's good enough to improve my value function. And now based on that better value function, I lock that in and I improve my policy. Based on that policy, I improve my value function. And this iterative procedure, again, you iterate until some convergence criteria. This is a lot like the kind of alternating directions optimization that we see in machine learning. So policy iteration often converges in fewer iterations than pure value iteration. So this is often kind of a preferred approach in a lot of cases. And again, I would like you to try on the game of tic-tac-toe, write a program to do value iteration, write another one to do policy iteration, and compare how fast they converge. Which one converges in less iterations? Which one's faster, on your CPU? So the last thing I want to point out is that the value function v, we're essentially optimizing the action to maximize this future expected reward, this expectation here. My reward now plus my discounted all sum of my future rewards. And when I compute my policy function pi, I'm trying to maximize over actions. I'm trying to find the action that maximizes this expectation. So it seems like there's redundant information. The value function and the policy function both are intimately depending on this expectation of all future rewards here. And so it turns out you can introduce something called the quality function, this Q function, which is the quality of being jointly in a state S and taking an action A. And literally, this quality function is that expectation from before. So this expectation that we're trying to estimate with our value function or exploit with our policy is the quality function. It is the expected current and future rewards given a state S and an action A. Now the Q function, it seems like I've just renamed something I've already worked with, and I have. But this is super, super important. Because when I did policy iteration and value iteration, I needed to have a model of what my future state S prime is so that I could use this value at that next state in my optimization, in my recursive dynamic programming optimization. Whereas in the quality function, if I start to learn a quality function Q of S and A, all of this information is implicitly in this function. And so I can optimize directly and learn and iterate this quality function, iteratively improve it, and I don't need a model for what my next state is because it's already implicitly defined in the quality function. That's a subtle point, but this quality function, just writing it so it's implicitly a function of the future state instead of an explicit function, means that I can do model-free reinforcement learning. I can optimize this quantity directly without knowing what my future state is going to be. I can do this by trial and error. And again, from this quality function, once I learn a good quality function, I can extract my value function or my policy pi from this Q function. So this has all the information I need to get my value function or my optimal policy. And so it's evolving that lots and lots of modern reinforcement learning algorithms really do rely on this quality function. So you have these deep quality networks that have been revolutionary in playing Atari games. So DeepMind's Atari game is a deep quality network. The early versions of like AlphaGo, use these quality functions. So really, really powerful stuff here. Okay, we've talked about this block here, where if we have a Markov decision process, we can do policy iteration or value iteration, leveraging dynamic programming and Bellman optimality. And we've also shown how this quality function Q kind of incorporates all of this information, but hopefully in a way that we can use for model-free control. So we'll talk about that later. All right, thank you.